Hi everyone, welcome to my channel. So today we are going to talk about load balancers. What are load balancers? You can think of them as the traffic cop of scalable systems. So whenever there are a lot of traffics to a system, what does a traffic cop do? The traffic cop simply makes sure that the traffic goes to appropriate locations or lanes so that the overall traffic is orderly and organized. And so what is a load balancer and why do we need them? So as I said, load balancer plays the role of a traffic cop in case of a distributed system. And when there is a lot of traffic coming to the distributed system, the load balancer makes sure the traffics are sent to the appropriate places. And it distributes incoming network traffic across multiple backend servers to optimize resource utilization and prevent overload. So these are very key points, which are resource utilization and prevent overload. So what is overload? When a lot of request is hammering on a particular node in a distributed system, that server can be overloaded with a lot of requests. Load balancers can prevent it. And also resource utilization. That means if there are some nodes in the system that are underutilized, load balancers can make sure that they are utilized properly so that the overutilized nodes are not hammered constantly. What are the key benefits of using load balancer? First comes high availability, definitely. As we talked about replication before, we can maintain multiple copies of the same data in a distributed system. And so what load balancer does is it helps in eliminating single points of failure. In case there are multiple replicas of the same data, then the load balancer on top can distribute the request to the data. And you also understand how it can help in the clients reaching the databases, right? We will talk about it in the next slide. And then scalability allows horizontal scaling by easily adding or removing servers based on demand. So load balancers can play the role of monitoring the traffic to the systems, which are the database servers in this case, and based on them, load balancer can make a decision to add or remove the servers on a high level. Then performance improves response times by evenly distributing load. And yeah, this is similar to preventing overload and the resource utilization and preventing server bottlenecks. And then efficiency maximizes the use of server resources, which is similar to what we talked about, the resource utilization bit. Now let's take a look at how the request flows when a system has a load balancer. We first have a client request. Client request reaches load balancer then selects the server, and then the request is forwarded to the server, and ultimately the selected server sends back the response. If I may sketch here, this is a client and it is sending a request, and instead of sending the request directly to the backend servers, the client requests are first handled by load balancers, and then there are a lot of servers in the backend, S1, S2, S3. So load balancer is responsible for choosing one of the servers for the request, and then forwards the request to it. Then server comes back with a response, and load balancer can forward the response to the the client. And then let's take a look at the key algorithms of how the traffic is directed. So you can see how load balancer chooses the server is a very important decision that we can take. One of the simplest algorithms is round robin. What is round robin? So let's say I can only choose between values 1, 2, and 3. So first time I will choose 1, second time I will choose 2, third time I will choose 3, and the fourth time again I will choose 1. And the loop goes on. So it distributes requests sequentially to each server. What is the benefit of it? It is very simple, and the load distribution is generally even. But there are some disadvantages to it as well. So when I said load distribution, what I meant was the number of requests that is distributed uniformly across servers. But what if all the requests are not same? There are some requests that are heavy and some requests which are relatively lightweight to perform. In that case, round robin doesn't work very well. Also, in case of maintaining a cache or the session, then round robin does not perform well, because you can imagine if client 1 uh, first time it connects to server 1, next time it connects to server 2, next time it connects to server 3, then the caching is meaningless. We need to cache client 1's data in all the servers, and the cache becomes so huge that it becomes unmaintainable. So yeah, there are some pros and cons, as with everything in life. Then list connection. So in this case, what load balancer will do, it will send new requests to the server with fewest active connections. So in this case, let's say the server 1 has one active connection, server 2 has one active connection, and server 3 has 3 active connection. For the sake of simplicity, let's make it 2. So in this case, server 1 has the least number of active connections, so server 1 will be chosen. Again, this tries to connect to a server which has more resources available based on the number of connections available to the server. But of course, there are some drawbacks as discussed earlier. Then we have the IP hashing, which directs requests from the same IP address to the same server. And this resolves the problem I was talking about, especially in maintaining the caches. So in this case, one client will always connect to one server. And of course, you can understand here that maintaining sticky sessions and appropriate caches are very easy, but this can lead to uneven resource utilization of the servers. And we also can talk about the weighted strategy, where the load balancer prioritizes servers based on their capacity. For example, weighted round robin. So in this case, the server is not chosen on round robin fashion or random fashion. Rather, they are chosen based on their capacity. The servers can expose some sort of metrics that the load balancer can read. For example, the CPU load, or in case the server is using some message bus, then the number of messages in the backlog for that particular topic. And then based on the capacity, whichever server the load balancer chooses, the request will be sent to that, and afterwards the response would be forwarded to the client. So let's talk about some types and architectures of load balancers. So what are the types of load balancers? So we can have load balancer at hardware level. So what are these load balancers? They are dedicated physical appliances that are connected to the servers. For example, we have F5 and then Citrix Netscape, and they deliver high performance, but they are also very costly. Then we have software load balancers, and they run on standard servers. For example, Nginx, which is a web server, but it can also be used as a load balancer or reverse proxy, HA proxy. These are flexible and cost effective. As you can imagine, we don't need to buy or rent a hardware, and running a software is generally less expensive. And then we also have cloud managed load balancers, which are provided as services by cloud providers. For example, AWS ELB, Google Cloud Load Balancer. And these load balancers are fully managed and scalable. So the cloud service provider takes care of the implementation of the load balancer, and as developers or system managers, we don't need to worry about exactly what type of load balancer it is under the hood in most of the time. And in terms of where the load balancer is implemented, we can differentiate between layer 4 and layer 7. Layer 4 is relatively low level, which is the transport level, and this is based on IP port, and this is faster or simpler. So whereas layer 7, this is implemented at application, and because it is implemented at application, we can do a lot more with this type of load balancing. For example, we can inspect HTTP headers, URLs, cookies, etc., etc. We can also take care of SSL termination, intelligent routing, using application level load balancing. So if we want to go for something simple strategy and we need a faster performance, then go with layer 4 at transport level. And at application level, generally the load balancing is required when the load balancing logic itself can be pretty complicated, which we can't implement easily in layer 4. So what are the key takeaways and when to use? So load balancing, as you can see, it is essential for distributed system itself. So in case of like we have applications where we require high availability, scalability, and optimal performance, load balancing is something that is very necessary. The load balancing can be applied on some cache, it can be applied on DB and other data related systems as well. Then we need to choose wisely to what load balancers we can use, selecting the right load balancer type and algorithm based on the application needs. For example, L7 for complex routing, which is at application level, L4 for speed, and also, as I discussed before, the routing algorithm should be selected based on our application needs. For example, should it be round robin, where we don't care which server the client talks to, or should it be somewhat sticky like IP based hashing? Yeah, we need to decide that based on the utility. Then integration often works with CDNs for static content, and crucial for modern deployment strategies, for example, blue, green, canary, and all that. So yeah, as you can imagine, so like let's briefly talk about how we can use load balancing for blue-green strategy. So in terms of blue-green deployment, whenever we have, let's say, a new feature, or there is a big improvement in the application logic, or data needs to be migrated, what we do is we maintain 2 copies of deployment for our same application. So this is green, this is blue, and whenever the requests come, the older version will keep on handling all the requests, where the newer blue version, it takes care of spinning up and then migrating the data. And after the blue becomes green, that means it is up and it is promoted from blue to green state, and in that case all the traffics would now be served by the new server. So there would be a load balancer on top of all this, which will understand the deployment status of the blue-green deployment, and based on that it will direct the traffic to the appropriate deployment. And beyond traffic, it provides benefits like SSL termination, basic security, DDoS protection, and rate limiting. One key thing to note here is that load balancing should not also be a single point of failure. What I mean by that is, if there is only one instance of load balancer deployed, in that case, if the load balancer somehow goes down, we will stop accepting traffic for the whole system, and that is not desirable. So generally what we do in terms of load balancer deployment itself is we follow something called an active passive deployment, where there is one load balancer instance which keeps on accepting all the requests, and there is another load balancer instance which is on standby and it does not accept any request. We make it redundant simply because if the active one it goes down, then the passive one takes the role of the active one, and we again create a new load balancer as the passive one in its place. So yeah, that's it for today in terms of load balancing. If you like my video, please like it, and also please subscribe to my channel and share the content with all the others. Thank you. See you in the next one.